Right? So let's think about bases. Right? Section 13.6, bases. We're going to look at an introduction. Bases are pretty much going to be the flip side of everything you're doing with acids. So bases, strong bases, are going to be hydroxides of the 1A elements, the alkali elements, the alkali earth or group 2A elements, hydroxides. So calcium hydroxide, also called lime, barium hydroxide, and strontium hydroxide. Now, I already warned you guys that this is only to the extent that it dissociates. So calculating the pH of a strong base, pretty straightforward. You're going to take your 5.25 times 10 to the minus 2 molar sodium hydroxide solution. The major species in solution are going to be our sodium, our hydroxide, and our H2O. Although the autoionization of water also produces hydroxide ions, the pH is going to be dominated by the hydroxide ions from the dissolved sodium hydroxide. So in solution, our hydroxide ion concentration is going to be the same as the sodium hydroxide concentration, right? Might be a little bit more because of the water, but you're talking like, 5.00001, right? The concentration of H plus we can get from Kw. So we can do H plus divided by K is equal to Kw over OH minus. So we're going to do 1 times 10 to the minus 14 divided by 5 times 10 to the minus 2. And we're going to get 2 to the minus 13 molar H plus, which means our pH is going to be minus log of 2 times 10 to the minus 13, or about 12.7. So for a basic solution for which the hydroxide concentration is bigger than the H plus concentration, your pH should be up above 7. You could have also done this by finding the POH and then doing 14 minus pH is equal to the 14 minus POH is equal to the pH. So the added OH minus from the salt has shifted the water autoionization equilibrium to the left, significantly lowering the H plus ion concentration compared to pure water. So again, we're still playing in water's playhouse, right? It's this Kw that has most of the stuff. And so as you increase the amount of OH, right, you bring this up to maintain Kw at 1 times 10 to the minus 14, your H plus concentration is going to be suppressed. Right? Here's how bases are going to react with water. Some of them are straight up going to produce OH minus, right? Our strong bases, lithium hydroxide makes OH minus. Strontium hydroxide is going to make 2 OH minuses per mole. What about some of these weak bases? Well, if you look, a lot of these are going to contain nitrogens with the lone pair of electrons up here. So methylamine, dimethylamine, trimethylamine, ethylamine, pyridine. These guys are going to be able to pick up a proton, right? And one of the places that they can pick up a proton from, so we're going to specify this weak base as a B for base, and then the water is going to act like an acid. Even though water is a very weak acid, it's the weakest acid there is, it's still able to have that proton removed. So your base is going to pull a proton off of water to form the conjugate weak acid, and you're going to be left behind with a conjugate base, but that conjugate base is hydroxide, which is a strong base. So we can write an equilibrium expression for this, and we're going to call it Kb because it's a base, and our Kb is going to be products, the conjugate acid, and hydroxide, over the reactants, the conjugate base. Right? They're going to compete with OH minus for the H plus ion, and our Kb values tend to be very small. So our Kb values for some common and weak bases, ammonia, which is really common, is going to have a conjugate acid of ammonium, and the Kb is 1 times 10 to the minus 5. Methylamine is going to have a conjugate of CH3 NH3 plus, so you've gained a proton over here. And its Kb is 4.3 times 10 to the minus 4. Something like alanine, another very common base, is going to have a C6H5NH2, and it's going to turn into C6H5NH3 plus, and its Kb is only 3.8 times 10 to the minus 10. Right? So remember what our relationship between Ka and Kb is that if we look at Kw, right, Kw is tied into the autodissociation of H plus and OH minus. If KB, right, is up here, and it is producing OH minus. And our Ka is producing H plus. Right? We are able to interconvert between a Ka and a Kb. So our Ka is going Kw over Kb, and Kb is going to be Kw over Ka. So it's very similar to the trick we just did a second ago, where we wanted to find out the H plus concentration. We took Kw, 1 times 10 to the minus 14, divided by the amount of hydroxide we have. So this relationship, right, is going to be important, and we're going to see why later on. It's mainly because we're going to have a table of Kas, and they're going to assume you can calculate a Kb from that. Right? Saves on paper. But if you wanted to know why your pH scale goes to 14, if I take pKa, 1 times 10 to the minus 7 for water, and pKb, which is going to be 1 times 10 to the minus 7 for water, and I take pKw, 1 times 10 to the minus 14. If I add 7 plus 7, I've got 14, and that's why your pH scale goes to 14. Let's do a concept check. We're going to calculate the pH of a 1.3 times 10 to the minus 3 molar solution of sodium hydroxide. Think about what you're going to do. A couple of ways to do it. I could convert this into OH minus, and then from OH minus use Kw over the OH minus ion concentration to find H plus. I could find a POH and then find a pH. Okay, let's see what you got. You should get a pH of 11. Right? And that makes sense because sodium hydroxide is a strong base, so you should be closer to 14 than you are to 12. Let's calculate the pH of a 1.3 times 10 to the minus 3 molar solution of calcium hydroxide. All right, pause for a second, come back. All right, it's 11.3. Why is it 11.3 and not 11? They're the same concentration, but remember that this calcium hydroxide is going to be CaOH2. And that's a very common trick that will show up a lot, is they'll try to trick you by throwing in this dihydroxide from one of these alkali earth metals and assuming people are just going to run that number and do minus base 10 log of that number, and they will end up getting it wrong. So watch out for this too, where they're trying to trick you on those bases. Let's do another one. All right, now we've got a 2.0 molar solution of ammonia, and they've given us a Kb. Is this a strong acid or strong acid, weak acid, strong base, or weak base? If they're giving you a Kb, you're going to need to recognize this guy as a weak base. If it's a weak one, you're going to need to throw in an ice table. All right, try to work through that ice table by yourselves, and then come back and let's see what we get. All right, you should have gotten a pH of 11.78. If you didn't do that one, that's okay. We'll do a little bit more review here. The pH calculations for solutions of weak bases are very similar to those for weak acids. We're going to need a couple of pieces of information. One is this relationship between Kw and ultimately pH and POH, and between Ka and Kb. Right, so let's calculate the pH of a 1 molar solution of methylamine, and they've given us a Kb, 4.3 times 8 times 10 to the minus 4. Since methylamine is a weak base, the major species in solution are going to be this methylamine and water. Both of those are going to be bases, but water can be neglected as a source of OH minus, so the dominant equilibrium is that between the methylamine picking up a proton from the water to form methylamide and hydroxide. This guy is a conjugate weak acid, right? And this guy over here, the conjugate base, is a strong base, though. So in the fight between a weak acid and a strong base, our strong base is going to dominate the pH. Our Kb expression is going to be 4.3 times 10 to the minus 4. And that's going to be our products over our reactants. We'll set up an ice table. We initially had 1 molar methylamine, no methylamide, and no hydroxide. We're going to lose a little bit of our conjugate weak base to form some conjugate weak acid and our conjugate strong base. We're going to end up with 1 minus x plus x and x. And so we're going to get Kb is 4.38 times 10 to the minus 4. That's equal to our products over our reactants. We will take our equilibrium values and replace them in as appropriate. And we're going to end up with x squared over 0.1. Does this look a lot like what you did with your Kas? Yeah, it does. So all of these are breaking down into very, very similar equilibrium problems. If you did the stuff in equilibrium chapter, okay, these guys are just specific cases, right? Kb is a specific kind of equilibrium. I don't have to worry about, something squared to the something cubed over something to the fourth, right? It's always going to have a very similar setup to this. You're going to find a value for x squared. They're making that simplifying assumption that x is small. And you get x is 2.1 times 10 to the minus 2. So the approximation is valid by our 5% rule.